How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the classic adventure of Archimedes, about the 3rd century BC, with some wondrous things to report. First, consider a body, a lead weight, which I hang on a spring scale, and the scale reads so much. I am not interested in what it reads, but it reads the weight of the body. Now let me submerge this body in a vessel of water, and we see a remarkable thing, a very remarkable thing. As I submerge it, the scale reads less and less and less, and I urge you to see that the weight is not resting on the bottom of the vessel of water. Accordingly, when I submerged the body, the water pushed up on it, provided a buoyant force, as we say, which Archimedes discovered in his classical bathtub experiment. Eureka, eureka, I have found it. Now, how much is the push up of the water on a body submerged? Archimedes said it this way. When a body is submerged in a fluid, that's either a gas or a liquid, we're talking liquids here. When a body is submerged in a liquid, it is buoyed up by a force equal to the weight of the liquid displaced. Now, I can prove that. Here I have a vessel which has an overflow spout, and I'm going to put a little water in it to be sure the water is up to the level of the spout. There it is. It's coming out there somewhat. And now I'll wait until it stops. The water is up to the level of the spout in this chamber. Now I'm going to get rid of that water. Now what am I going to do? I'm going to submerge this body in that chamber of water, and as anyone in his right mind would recognize and attest, will not some water be pushed out? Indeed, and I'm going to push some water out and catch it in that little bucket. Watch it now. And of course, again, the scale will read less, but I'm not interested in that this time. I'm interested in the water that gets pushed out. Watch it now. And I'll wait till all that's going to be pushed out is pushed out. That's good enough. Now, what would I do with these adventures? Well, first I would have noticed how much less the scale read when the body was submerged in the liquid. Suppose it read less by 10 grams. Then I weigh this water in this bucket. And what would the water in this bucket weigh? 10 grams, meaning that the body was buoyed up by a force equal to the weight of the water this body displaced. Archimedes' principle. Fantastic. Now, I said that the water pushes up. I'm going to prove that. Indeed, you should recognize it already from your adventures by the sea. When you walk into the ocean, do you not discover that the deeper you go, the less push your feet have on the earth below, because the water is buoying you up more and more the deeper submerged your body becomes? Here I have a glass and a hole in the very bottom, and I'm going to push the glass down. The evidence that the water pushes up will be witnessed by the water coming up into that hole. Watch it. There it is. There it is. And I say the water pushes up. I'm going to prove that in another way. Here is a glass tube and a plate on a string. And I'm going to put the string through this glass tube. And now I'm holding the string in hand. And obviously, since the plate has weight, if I let go of the string, the plate will fall down. Watch it. Well, of course, says anyone who's watching. Doesn't that professor know that if you let go of the plate, it'll fall down? Of course it'll fall down. Now I'm going to prove again that the water pushes up. Well, how? I'm going to put this into the water, and instantly I make connection with the water. I'm going to let go of the string. When I let go of the string out here, the plate fell off. The plate will not fall off in there. Watch it. There it is. And you see water rushing into the inner cylinder, climbing higher and higher, and everybody says, well, when it gets the same height inside the vessel as outside the vessel, then the plate will fall off, and I'm going to leave that for you to think about. But now, my new adventure, Archimedes bucket and cylinder. I have here a little bucket, very nicely formed, and a solid cylinder which fits it exactly, And here's what I'm going to do. I'm going to balance this bucket. I'm going to balance that bucket with the cylinder below. Let me see if I can represent that. Here is the cylinder below. And remember, that solid cylinder fits that bucket exactly. And I'm going to balance this with some weights over here. Put the beam balance in equilibrium. Then what am I going to do? I'm going to come up underneath with a vessel of water in this fashion. Vessel of water, so that I submerge the solid cylinder. The equilibrium in the balance will be destroyed, as we might say, because why? The water here is pushing the cylinder up. How much is it pushing the cylinder up? It is pushing the cylinder up with a force equal to the weight of that water displaced. And how much water is displaced? The volume of the cylinder. And how much is the volume of the cylinder? The volume of the cup. Accordingly, with the equilibrium destroyed because there is a lift or buoyant force here, I am now going to pour some water into this little bucket. Water, 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 water. Oh, ho. When this bucket gets full, what will we see? An absolutely enchanting thing. We will see the equilibrium restored. Now I have such a bucket and cylinder. There's the cylinder, there's the bucket, and I have put it in equilibrium on the scale. Now I'm going to bring up this water and submerge the lower solid cylinder. I hope you see that the equilibrium has been destroyed. The balance is no longer in balance. Oh, I came up too high. Now I am going to fill the little bucket. I'm having a little trouble here being steady. I'm going to fill the little bucket, and the equilibrium, which does not now exist in the scale reading, will be restored. Watch me now. Oh, I filled it over much, and there's a very high meniscus. So, Archimedes bucket and cylinder. The proof is very beautiful. A body is buoyed up by a force equal to the weight of the water displaced. Now, regarding buoyant forces and bodies that sink and bodies that float, here is a vessel of water and here's a piece of wood. Floats. Here is another piece of wood. Wood, water. Huh, heavier than water. Lignum vitae. Here is a piece of wood. Heavier than water. So there are woods that sink and woods that float, their densities being less or more than that of water. Now, regarding bodies submerged in liquids, I have here something absolutely enchanting. Here is a vessel of water in which I'm going to put a wooden ball. There. It sinks about, I don't know, 5/8 or something like that. Now, here is a vessel of mercury. Vessel of mercury. I'm going to put the ball in the vessel of mercury. Watch it. It doesn't sink at all, hardly. Hardly. It rides on the very surface. But that's wood. Very light. How about steel? Oh-ho! You know that the specific gravity of steel is about 7 or 8. The specific gravity of water is 1. You know that steel sinks in water. Watch it. Sinks to the bottom. By the way, I say steel sinks in water. On an earlier program on surface tension and the strange behavior of the free surfaces of liquids, I showed in a demonstration where I float a steel needle on water. So steel can be made to float on water. But how about the steel ball in the mercury? Watch it. Oh, this is something. There it is. There it is. The steel floating on the mercury. This is a marvelous thing. Let me use a larger steel sphere, because this is enchanting to see. There it is. Steel floating in mercury. Now, talking about Archimedes leads me to show you a classic mosaic. You remember that Archimedes defended the city of Syracuse when it was attacked by the Romans under the general Marcellus. And then Archimedes was put to death by a Roman soldier who ran upon him while he was doing a demonstration in the sand. So here is that mosaic, which I hope you will see. There is the Roman soldier urging Archimedes, "Come to my general Marcellus." And Archimedes begged him, "Let me finish first my demonstration." And here is another monument to Archimedes, which shows him holding a mirror. This is a little glossy and hard to see. Holding a mirror with which, you remember, he set fire to the enemy ships far from shore. So, what have we discovered here? The remarkable principle of Archimedes that a body submerged in a liquid is buoyed up by a force equal to the weight of the liquid displaced. Now, Archimedes, as you know, apart from being a natural philosopher of the first magnitude, was also a mathematician. And I want to tell you quickly about some things he discovered of a mathematical nature, because they are enchanting. And here they are. Here I have a right circular cylinder, and here I have a right circular cone, and here I have a sphere. They are the same altitude and the same radius. And what did Archimedes discover? He discovered, by playing with these, filling them now in turn with sand, that the volumes were uniquely related in the ratio of 1 to 2 to 3. I'll leave it to you to discover how that ratio goes with respect to the bodies. Now, in his later years, having made many discoveries of great moment and significance, he was asked what he viewed as his greatest, and he referred to this: the ratio of the volumes of the cylinder to the cone to the sphere, and asked that when he dies, such a matter be put atop his tomb, which shows a cylinder, a sphere circumscribed by a cylinder. So here is a sphere about which is circumscribed a cylinder, and this was put on top of Archimedes' tomb, buried near Syracuse. Where are we then in this dialogue? Archimedes, 3rd century BC, who must certainly rank with Newton of the 17th century and Einstein of the 20th. So next time you go to the sea to bathe, remember Archimedes. And when indeed you take a bath in your bathtub and you submerge yourself in the water and the water rises, remember the affairs here, which revealed that beautiful fact which we use abundantly, because after all, this is why ships can sail on the sea and submarines under the sea and airplanes above the sea. And I thank you for your attention.